Welcome to the Honeywell RDR-4000 IntuVue Weather Radar Pilot Training webinar for Boeing Aircraft. I'm Steve Hammack from the Customer Product Support Group. Just a reminder that this presentation is Honeywell proprietary information and is subject to export restrictions. In this training, we will compare the RDR-4000 to conventional radar, look at the heart of the system, the 3D volumetric buffer, and the operational modes it provides. At the end, we'll pull it all together by showing some operational examples and in-service experience. For operators that have the optional hazard display features installed, there is a separate training module available on mygdc.com covering those features. The RDR-4000 is much easier to use, but it's different. It automates many of the tasks required by conventional radar, but does them in a different way. So a good starting point would be a quick review of a conventional tilt-based radar operation, and then we'll see how the RDR-4000 makes life easier. With a conventional tilt-based radar, the system sweeps an area ahead of the aircraft based on the selected tilt angle. There is a one-to-one correspondence between the antenna sweep and what is shown on the display. It provides reflectivity information in two dimensions, azimuth and range. For detection, most crews use a technique called the cruise ground park technique, or could be referred to as establishing a protection zone. Whatever it's called, the technique is the same, lowering the beam until ground returns appear at the outer edge of the display. The technique has two main benefits. First, storm cells are easily identified because they walk out of the ground returns. And secondly, if there isn't a radar shadow behind the cell, then we know the radar signal hasn't been attenuated. This technique detects all cells, but analysis is still required in order to make a deviation decision. For analysis, we manipulate the tilt control and build a mental picture of the weather ahead. The vertical extent of the cell can be determined using the 1 in 60 rule. Remember the 1 in 60 rule from early navigation training. If you are 60 nautical miles from a VOR station and 1 degree off track, you are 1 nautical mile off track. For radar, there's an easier form of the rule. Just take the range, add 2 zeros, and that will tell you how many feet 1 degree is at any range. For example, at 60 nautical miles, add 2 zeros, and 1 degree at 60 nautical miles is 6,000 feet, which is very close to 1 nautical mile. At 40 nautical miles, 1 degree is 4,000 feet. An air transport antenna has a 3-degree beam width, so at 40 nautical miles it is 3 times that, or 12,000 feet tall and wide. This simple rule can be used in several ways. First, the beam is extremely large at long ranges. At 320 nautical miles, it is over 96,000 feet tall and wide in this example. Second, close to the aircraft, the beam is very narrow, and at high cruise altitudes is entirely in less reflective frozen ice crystals. This also explains why a cell detected at longer range requires continuous down tilt to track the cell as it gets closer, or it will disappear under the beam as it gets narrower. And lastly, it can be used to measure the height of a cell. To explain, here's a quick example. The aircraft is in cruise flight at 38,000 feet and the cell is detected 40 nautical miles ahead. The analysis will be done relative to the aircraft altitude of 38,000 feet. Start by raising the tilt 1/2 of the antenna's beam width, or 1.5 degrees for the 3-degree air transport antenna used in this example. That puts the bottom of the beam parallel to the flight path. Now raise the beam until the returns begin to disappear. Keep in mind the aircraft is at 38,000 feet. Tilting up will cause the radar to look mainly at less reflective frozen ice crystals. The gain can be increased to maximum, allowing us to better see the frozen particles and get a better measurement of the height of the cell. Now, increasing the tilt may be continued until the top of the cell disappears. The cell completely disappears at plus 3.5 degrees up tilt. The exercise started at plus 1.5 degrees, so the beam was raised a total of 2 degrees. At 40 nautical miles, 1 degree is 4,000 feet, so the beam was raised a total of 8,000 feet. The aircraft is at 38,000 feet, so the wet top of this cell is at 46,000 feet. The course of action in this case is obvious. The cell directly ahead should definitely be avoided since the wet top exceeds the aircraft altitude. There is always a trade-off when making a deviation decision. Analysis should be completed allowing enough time to negotiate a deviation with ATC, but close enough to the weather to have adequate resolution for effective analysis. At 40 nautical miles, 1 degree is 4,000 feet. At 80 nautical miles, it's 8,000 feet, and at 100 nautical miles, it's 10,000 feet. For cases where the cell is much higher or lower than the aircraft, it isn't an issue. The in-between cases are much more difficult to evaluate. Before moving on to the RDR-4000, a discussion about reflectivity, which is what a radar measures, is in order. Radar does not directly measure rainfall rate. It measures how much of the transmitted energy is reflected back to the radar. The amount of reflected energy is proportional to the rainfall rate and is represented by the different colors on the display. The problem is that rain is not the hazard that needs to be avoided. What really needs to be avoided is a turbulence associated with convective activity. So then, why do we even look at the colors? The colors give us some indication of the probability of turbulence and hail size. In the chart on the left, at the beginning of red, 40 dBz, it indicates a 40% chance of moderate turbulence and a 5% chance of severe turbulence. The same with hail size probability. This isn't the probability that there will be hail, but rather if there is hail, what size it is likely to be. It can be said that probability in statistics is the science of proving nothing. If there is a 40% chance of moderate turbulence, that means there is also a 60% chance there isn't. Well, there is a 100% guarantee that a flight through this cell would encounter turbulence. At the bottom of the previous chart, there was a note stating the chart was for convective weather. So there is a need to first determine the weather in question is convective for the chart to apply. And so the radar should be used as a tool to detect convective activity, not just rainfall. Convective activity is detected by looking at the vertical development or extent of cells and how much moisture is carried aloft. So altitude is the important third dimension. Conventional radars only provide range and azimuth information. The RDR-4000 captures altitude information and uses it in the automatic detection and manual analysis modes to provide additional information to assist in making deviation decisions. The RDR-4000 is subject to the same physical limitations as a conventional radar, but it provides modes to help reduce workload. As the description of the RDR-4000 progresses, note how altitude information is used to help the pilot make informed decisions. This module will examine the heart of the RDR-4000 system, the 3D volumetric buffer. One of the first things a pilot will notice about the RDR-4000 system is there is no tilt control. The system automatically and continuously scans and collects weather and ground returns from the nose of the aircraft out to 320 nautical miles and from the ground to 60,000 feet. For scans above the freezing level, the system automatically increases the gain to make less reflective frozen stormtops more visible. The scanned information is stored in a 3D volumetric buffer, or memory, and is continuously updated and compensated for aircraft movement. The data is also corrected for the Earth's curvature, so the altitudes displayed by the system are true MSL altitudes. If left uncorrected, the effect of the Earth's curvature can be quite significant. In the picture shown, the aircraft is at flight level 250. However, because of the Earth's curvature, the center of the beam is above 27,000 feet at 60 nautical miles, almost 37,000 feet at 120 nautical miles, and 44,000 feet at 150 nautical miles. The automatic scanning stores all of the weather and ground return information in the 3D buffer memory. The system also contains an internal worldwide train database that is a version of our EGPWS database, but without airports, runways, and obstacles. Because the RDR-4000 uses only the train information, regularly scheduled updates are not required. The train database allows the radar to distinguish between weather and ground returns. This allows the display of only weather information in the weather modes and only ground returns in the ground map mode. In the ground map mode, the ground returns are provided by the radar returns and not the internal terrain database. This allows for an independent verification of position. Other information put in the 3D buffer includes enhanced turbulence data. Turbulence detection is automatic and is provided out to 40 nautical miles for any range selection in auto mode. The RDR-4000 is the first system certified to the FAA's new Enhanced Turbulence Minimum Operational Performance Standard, or MOPS. It provides more sensitive and accurate turbulence information with fewer false alerts and improved correlation to predicted aircraft G-forces. It is up to 12 times more sensitive than current systems and is displayed plus or minus 5,000 feet around the aircraft's altitude. Think of the 3D volumetric buffer as a giant Rubik's Cube. Each square is at a certain position in range, azimuth, latitude, longitude, and altitude. In each of these squares, information is stored about reflectivity, turbulence, and if the return is from weather or ground. Since there is no tilt control, the pilot is not using the control panel to control the radar, but rather using it to request information from the 3D buffer. This information can be presented in many ways, including comparing the buffer to the aircraft's flight path and displaying the weather on the flight path in solid colors as shown here, and weather outside of the flight path is displayed in a different pattern as shown here. This display is from a different display system, which includes a vertical display of weather. Shown here is an example to illustrate how weather on and off of the flight path is shown on the nav display. The pilot can also extract altitude slices out of the buffer, corrected for the Earth's curvature, and display them on the ND. Here we have the same storm cell with slices extracted at 14,000 feet and 27,000 feet. This analysis mode provides a simple means for making deviation decisions. This module will describe the operational modes provided by the 3D buffer. The auto mode will be discussed first. The auto mode is the automatic detection mode of the radar. In auto mode, the system analyzes the data in the 3D volumetric buffer and compares it to the aircraft's vertical flight path. It then shows weather in the flight path in a solid pattern and weather away from the flight path in a hashed pattern. Here are some examples. In the first one, the aircraft is straight and level below 25,000 feet. Both storm cells are a threat based on the flight path, and the display would look like a normal radar display with both cells displayed in solid colors. The normal envelope around the flight path is plus or minus 4,000 feet for weather. Turbulence information is displayed plus or minus 5,000 feet around the aircraft's altitude. Now the aircraft begins a climb to cruise altitude. The cell closer to the aircraft is in the flight path envelope and is still shown in solid colors, but the second cell is way below the flight path and will be shown in a hash pattern, indicating it is outside the flight path. Flight path is determined by using vertical rate and ground speed, and is extrapolated out to 60 nautical miles because we don't assume the aircraft will climb or descend forever. At 60 nautical miles, that altitude is used as the altitude beyond 60 nautical miles. In this example, the aircraft is at cruise altitude but beginning a descent. Based on the new flight path, the second cell will now change from the hash pattern to the solid pattern, indicating that it is now in the aircraft's flight path. The normal envelope around the aircraft is plus or minus 4,000 feet. However, when the aircraft passes through 25,000 feet, the bottom of the envelope becomes fixed at 25,000 feet and goes to 4,000 feet above the aircraft altitude. Most inadvertent turbulence encounters, especially at night, are due to less reflective frozen stormtops. The RDR-4000 system does several things to make these cells more visible. First, in the collection process, the gain is increased when scanning at higher altitudes. Second, the floor of the flight path envelope never goes above 25,000 feet. And third, what is displayed is the maximum reflectivity at any point from 25,000 feet to 4,000 feet above the aircraft altitude. This concept is very similar to the National Weather Service images. They provide two types of reflectivity data called base and composite reflectivity. The image shown is a base image. Think of this image as showing the rainfall at the surface. On a base scan, the system uses a single tilt angle and shows the base reflectivity data. What is shown here is a single base scan on a column of weather, outlined in blue, that would result in green being displayed. A composite image is collected over many sweeps. In the next scan, the reflectivity is increased and would be yellow. In the next scan, the reflectivity is increased further and is red. In a composite image, the maximum reflectivity in the entire column is used. So in the left column, the maximum reflectivity is yellow, in the center it is red, and on the right, green. Think of a composite image as a worst-case image. It is showing the worst possible weather or maximum reflectivity in a given volume. This is the result of a composite image for the same area. Looking at them side by side, the composite image shows more returns as expected. Base reflectivity is useful for showing where it is raining on the ground, but since airplanes don't fly at ground level, it is more useful to see what is happening at higher altitudes. And this is what the 3D volumetric buffer essentially shows, composite reflectivity. But some enhancements have been added to help since airplanes fly at a wide range of altitudes. To better explain this concept, here is an example of a typical storm cell. The solid lines in this cross-section represent isoecho contours or lines of constant reflectivity. At the top of the cell, the reflectivity is only 20 dBz and would normally be shown as light green on the display. Notice the arrows in the picture. They represent the wind speed and direction within the cell. At the bottom, there is inflow into the cell, but look at the top. The arrows near the top of the cell are the longest, indicating they have the strongest updraft velocities, but would only appear as light green on the display based on the 20 dBz contour line. This is what it would look like on a legacy radar system. Close to the cell, the beam is very narrow and intersects the cell at high altitude where the frozen particles are less reflective. Even though this cell had enough energy to lift moisture over 37,000 feet into the atmosphere, it would only show up as light green on the display. At cruise altitudes, for any given point on the display, the RDR-4000 looks into the buffer from 25,000 feet to 4,000 feet above the aircraft altitude and extracts the maximum reflectivity for each point on the display. So in the case of this cell, instead of just showing light green on the display, the RDR-4000 would show green, yellow, and red, alerting the pilot of the hazardous condition. The area above 25,000 feet is shown in solid colors for flight path weather, and the same thing happens for the secondary weather. The maximum reflectivity of the secondary weather is shown, but in a hashed pattern. Flight path weather always has priority over and covers secondary weather. So if there is hash red below and solid green above, the red will be covered by the solid green. Because the pilot will see more weather presented in a composite image compared to conventional radar, there may be times when it appears the system is oversensitive. But the key is to always think about altitude first and then color. What the system is telling the pilot is this cell had enough energy to push moisture over 25,000 feet into the atmosphere. The solid flight path color doesn't necessarily mean that you will need to avoid this weather. It means the weather has penetrated your protection zone, should be monitored, and may require analysis. And for the same reason, it might appear at times the system isn't sensitive enough. In this case, the height of the cell has been decreased, so the pilot only sees green above 25,000 feet. But remember, the flight path weather always has priority over and covers the secondary weather. So the flight path weather, which is green, covers the yellow and red at the lower altitude. But again, use the key. Think about altitude first, then color. The system is telling the pilot this cell has moisture above 25,000 feet, has entered your protection zone, and should be monitored. So how do you make your deviation decision? In a moment, we'll discuss man mode and later on show some practical examples how it can be used in conjunction with auto mode to make effective deviation decisions. This is a more graphical representation of the auto mode. The translucent wedge indicates the plus minus 4,000 foot envelope around the aircraft. Here the aircraft is flying straight and level, and where the wedge intersects the cell in front of the airplane is shown in a solid pattern. The low-lying weather off to the left is still shown, but in a cross-hatched pattern. This table is in the pilot's guide, and while it looks somewhat daunting, it's really fairly simple. The normal flight path envelope is plus or minus 4,000 feet around the aircraft's flight path. As described, the bottom of the envelope never goes above 25,000 feet so that frozen stormtops are more visible. When the aircraft reaches 29,000 feet, which is 25,000 plus 4,000, the bottom of the envelope stops at 25,000 feet. Likewise, on takeoff, approach, and landing, the top of the buffer never goes below 10,000 feet, which is 6,000 plus 4,000. This allows about 10 minutes look ahead along the flight path. Now let's look at the manual analysis mode. It's called man mode on the Boeing aircraft. This mode allows the selection of horizontal slices from the buffer that are corrected for the Earth's curvature, so they are true MSL altitudes. The captain and first officer can have different altitude slices selected. The initial slice will be at the current aircraft altitude and then can be dialed up or down from 0 to 60,000 feet in 1,000 foot increments. The selected altitude is maintained regardless of whether the aircraft is climbing or descending. For altitudes below ground level, nothing is shown on the display. In these pictures, the same area of weather is displayed at different altitudes via altitude slices. On the left, a slice is taken at 14,000 feet, and on the right, a slice is taken at 27,000 feet. This mode allows the pilot to easily measure the tops of the cells to find a deviation path, while never having to manipulate tilt or perform mental math. With a conventional pencil beam antenna, the radar would display just a narrow swath of ground returns. The RDR-4000 pieces all of these narrow swaths together in the buffer to give you an extended ground map. Ground map is optimized for longer ranges and weather returns are suppressed. However, over areas with very low reflectivity like water, some weather returns may appear. Map mode is useful for identifying prominent features like coastlines and lakes. The ground returns are actual radar reflectivity and not from the internal terrain database. This provides an independent verification of position. Ground map mode can also be used to identify areas of attenuation. The two pictures shown are from the same area. The picture on the left shows weather with ground returns suppressed. Picture on the right shows a ground map with the weather return suppressed. Notice the areas where the ground returns cannot be seen, indicating attenuation or radar shadowing. The weather here is strong enough the radar beam cannot penetrate any further, so the storm might be worse than it looks or may extend further than it appears. Normal operation is very straightforward. You'll be in auto mode most of the time, and range selection varies with phase of flight. In most cases, detection and avoidance can all be done in auto. Think of auto mode as your protection zone. Not all weather shown as flight path will need to be avoided, but it should be monitored and may need analysis. The man mode will aid you in your analysis in selecting a deviation path. Turbulence information is only shown in auto mode so that reflectivity information can be observed in the man mode during analysis. Here are a few simple examples to make sure the auto and man modes are understood before we look at some real-life operational examples. In this example, the radar is in auto mode, and the aircraft is flying straight and level at 20,000 feet. There is weather from 60 to 80 nautical miles ahead. So what would the pilot see on the display? The first thing to remember is the envelope is plus or minus 4,000 feet around the aircraft, or from 24,000 feet to 16,000 feet. Since this is outside of the flight path envelope, the weather is shown in a crosshatch pattern. Now let's go to the man mode and look at an altitude slice. Remember, when the manual mode is selected, the initial slice is at the current aircraft altitude, or 20,000 feet in this example. So what would the pilot see on the display? Nothing, because the weather is above the selected altitude slice. An easy way to think about this is, in the auto mode, all of the weather is displayed. It is just separated into flight path and secondary weather. In the man mode, only the weather at the selected altitude is displayed. Now select an altitude slice at 39,000 feet. What would the pilot see? He would see the weather above the aircraft altitude. Here's another look at auto mode, but this time the aircraft is at flight level 390. Remember that the bottom of the envelope never goes above 25,000 feet and goes to 4,000 feet above the aircraft altitude, so it extends from 25,000 feet to 43,000 feet in this case. So what would the pilot see? He would see solid green from 60 to 80 nautical miles because it is in the flight path. The red was purposely made smaller than the green to illustrate a point. The flight path weather always has priority over and covers the secondary weather. Remember, the system is giving altitude information. It is showing there is weather above 25,000 feet. So always think about altitude first, then the color. The aircraft is now at the same altitude, but the picture has changed slightly. So what would this look like on the display? From 60 to 80 nautical miles, it would look the same, but where the secondary weather isn't being covered by the primary flight path weather, it is shown, but in a crosshatch pattern. So here it is showing weather in and outside of the protection zone. Now the weather is the same, but the aircraft has reached the top of descent point and has started a descent. What would the picture look like now? Since the aircraft is now descending, the flight path changes, and so will the picture. The red is now in the flight path and covers the green, which is now secondary to the flight path. It isn't necessary to memorize the altitudes the system is using, as long as there is a basic understanding about what the system is doing and showing the pilot. If there's ever a doubt about what the system is displaying, use man mode and look at altitude slices and build up a mental picture of the weather. Now let's look at some real-life operational examples. Recall that all radars are subject to line-of-sight limitations. The red area in this picture shows where the radar's energy is blocked beyond the horizon due to the Earth's curvature. The radar line of sight, or radar horizon, varies with altitude and is approximately 200 nautical miles at 26,000 feet and 250 nautical miles at 41,000 feet. Even though the radar energy is blocked, we can use this to our advantage. Anything that shows up beyond the radar line of sight is significant and should be monitored. But at this distance, deviation decisions are not being made. The weather at this range should be viewed on a more strategic basis. By the time the aircraft reaches these cells, they may have moved into or out of the flight path, increased or decreased in intensity, or completely dissipated. At long ranges, all the pilot knows is they are worth monitoring. At long range, the beam is extremely large, so everything will be shown as flight path weather since there isn't adequate resolution to separate it into flight path and secondary. But again, this should not be an issue because at this distance, the weather should only be considered strategically. As the weather gets closer, it will separate into flight path and secondary weather and provide adequate resolution for analysis. So let's look at a couple of examples using the analysis capabilities of the radar. In this example, the Honeywell 757 is level at flight level 400 over Louisiana. There are some cells with low tops and low reflectivity near the aircraft which are non-threatening. 120 nautical miles ahead, there is some yellow reflectivity that warrants attention. The auto mode display is on the left, and on the right side, a constant altitude slice is being displayed at the aircraft's flight level. In this particular scenario, the fact there is not much difference between the two displays beyond 80 nautical miles doesn't necessarily mean all this weather is at flight level 400. It just indicates that given the resolution at this range, this is the weather that can be separated from the ground clutter. As the aircraft gets closer to the weather, the radar detects what looks like a patch of stratiform weather to the left. On the right-hand display, a constant altitude slice at the aircraft's flight level indicates there is little reflectivity aloft in that area that would indicate a potential hazard. Remember, in auto mode, the maximum reflectivity from 25,000 feet to 44,000 feet is being displayed. The constant altitude slice is showing the reflectivity at 40,000 feet. The convective area ahead is showing two distinct cells. The apparent increase in reflectivity from the previous slide is caused by two factors. One, the radar is now able to distinguish the difference between weather reflectivity and ground clutter as the aircraft gets closer to the weather. And two, the radar can now resolve relatively small pockets of higher reflectivity because the beamwidth resolution is improving. At this point, the crew should expect the two cells ahead will require some type of avoidance maneuver. All other displayed weather is of no consequence. The range is now 80 nautical miles, as the cells to be avoided are at about 70 miles. A look at the altitude slice on the right-hand display indicates the cell on the right appears to be carrying a little more reflectivity aloft than the cell on the left. The auto mode display is also showing a patch of yellow reflectivity immediately to the left of the two cells. But analysis using constant altitude slices indicates the bulk of the reflectivity from this feature is not seen until about flight level 300, which reduces the threat level somewhat. Given the wind direction of right to left, the pilot should be planning a deviation to the right side of the two cells, which makes any reflectivity to the left of no interest. However, there is some weather to the right coming into view near the deviation path that will need to be monitored. 20 miles closer, the cell on the right is showing much more reflectivity, and a look at an altitude slice shows it is the only cell that is a hazard at the aircraft's flight level. The weather to the right of the two cells in the deviation path has developed into nothing of interest. When the cell is at a range where turbulence can be measured, additional evidence comes into view, the magenta color, indicating the cell on the right is the most important one to be avoided. A constant altitude slice at flight level 350 shows a clear corridor on the right-hand display for deviation around the weather. Here's another example to illustrate how the auto and man modes are used to analyze and avoid convective weather. It will emphasize the use of constant altitude slices to analyze a line of convection in order to find an avoidance path. The aircraft is level at flight level 370 over Texas. On the 320 nautical mile range scale, there are two parallel lines of convective weather. The line at longer range looks rather impassable, but because the example is an actual flight test, the 757 crew will use auto and man modes to find a suitable path through the closer line. The 320-mile display gives the big picture situation. The 160-mile display gives more detail on the closer line of storms the crew will analyze to find a deviation path. The auto mode picture by itself doesn't seem to provide much hope, but looking at an altitude slice at flight level 370, there are two small, higher reflectivity cells on each side of the aircraft's track. Looking a little higher with a constant altitude slice at flight level 400, there appears to be a potential way through. These cells are still more than 120 miles away, so there remains considerable ambiguity regarding the precise ecotop of any part of the weather. But so far, the analysis shows a weak part of the line directly ahead of the aircraft. The line is now just outside 80 miles, and the 757 has climbed to flight level 420. Again, the auto mode alone might be interpreted to indicate there is no path through. Looking at an altitude slice at flight level 400, the analysis shows that most of the action is to the right of track, and the potential path through is persisting. The cells in the example are now at 60 nautical miles, and looking at an altitude slice at flight level 330, there appears to be a low reflectivity path for the aircraft to go through. In this particular scenario, it probably would have been easier and safer just to go around this line to the right, but it provided a useful example demonstrating how to effectively use analysis to determine a deviation path. Now we'll look at some in-service experience. This will help us understand and deal with some common weather issues. In the examples just shown, the left-hand display was in auto mode while the right-hand display was in man mode. This is a good way to use the system. Even if radar is only selected on one display, the pilot can switch back and forth between auto and man modes. Looking at altitude slices can also help deal with areas of stratiform weather. Remember, in the auto mode, the normal envelope is plus minus 4,000 feet around the aircraft, but when the aircraft climbs above 29,000 feet, the bottom of the envelope never goes above 25,000 feet. In some parts of the world, high stratus layers may be encountered that will sometimes exceed 25,000 feet. Since the layer is above the 25,000 foot floor of the envelope, there could be a large area of green, yellow, or red on the display shown in solid colors. The stratus can be fine to fly through, but it is more difficult to see embedded cells within the stratus. An easy way to handle this problem is to have one side in auto mode and the other side in man mode, looking at a constant altitude slice. Then select an altitude slice just above the stratus layer to see any embedded cells within the stratus. So here's the stratus layer, and the yellow line represents an altitude slice above the layer where the embedded cell is now clearly visible. The opposite, but similar situation could occur during descent and approach. As you descend and your flight path changes, the cell ahead of you will now become flight path weather, and the large area of high stratus will now be shown as secondary weather in the crosshatch pattern. Using man mode, you can declutter the display by selecting altitude slice below the stratus layer, again making the cell more apparent. Here's another example where man mode can help aid in evaluating the weather situation. As we mentioned at the beginning, the RDR-4000 is subject to the same physical limitations as conventional radar. The picture on the top left shows a stratus layer below the 25,000 foot boundary. The picture below that is a digital representation of the stratus layer, or a series of cells all the same height. Close to the aircraft, the beam is narrow and provides very good resolution for measurements. But as the range increases, the resolution gets progressively worse and affects the accuracy of the measurements. This causes an apparent increase in the height of the cells, or in this case, the stratus layer. This can appear on the display as a halo or ring of secondary weather returns fixed around the aircraft. In this picture, the ring extends out to approximately 37 nautical miles. At longer ranges, the weather is showing up as flight path weather because its decreased resolution causes the stratus weather to encroach into our 25,000 foot boundary. But as the weather gets closer and the resolution improves, it becomes secondary. A quick look at altitude slices would show the expanding stratus layer, but more importantly, the convective cell at about 65 nautical miles ahead. As mentioned earlier, flight path weather should be thought of as your protection zone. You may not need to avoid all weather shown in the solid pattern, but it should be monitored and analyzed. If there is ever a doubt about what the auto mode is showing, the man mode will help build a mental picture of the weather around the aircraft. You'll be in auto mode most of the time, and for isolated cells, the pilot can plan avoidance without leaving auto mode. But for cases where the pilot needs to analyze the weather and pick a deviation path, the man mode should be used to perform the analysis. Remember, the auto mode is for the automatic detection of weather. The altitude slices are for analysis. Let's look at a couple of things that are often misunderstood about X-band airborne weather radar systems. These radars are designed to reflect off water droplets of sufficient size and quantity. They do not detect water vapor, clouds, fog, volcanic ash, or extremely dry hail and snow, or clear air turbulence. Rain, wet hail, and wet snow are very good reflectors of radar energy. But dry hail, for example, only returns about 3% of the energy that a raindrop returns. At times, pilots may see a cloud mass and think that it should be shown on the radar display. Large white puffy clouds may be a developing storm cell, but they will not show on the radar until there is a sufficient size and quantity of water droplets available. Somewhat less obvious, immediately after a storm cell is dissipated and little to no rain is falling, a dark cloud mass may still exist that hasn't broken up yet due to the wind. The pilot can try increasing the gain to see if they are just below the green threshold, but there may not be enough reflectivity available. If there is ever any doubt the radar is working properly, a great way to check is by using the radar Radome competence check. This will verify the radar is functioning and identify any issues with the Radome. It's very simple to do. At cruise altitude, select map mode and notice how far out the radar will paint ground returns. This will vary somewhat depending on altitude and the type and elevation of the terrain below. If ground returns aren't visible, or there are areas where the returns are missing, it could indicate a radar or radome problem. Also, if the radar can normally paint ground returns out to 180 nautical miles, but can now only paint returns to 80 nautical miles, or on the left side of the display, the radar can paint to 150 nautical miles, but on the right side of the display, it can only paint to 50 nautical miles, there could be an issue. Another item related to reflectivity that pilots observed when they first started using the new system was magenta turbulence indications in black areas. The reflectivity chart in this picture illustrates that black doesn't mean it's not raining. It's just raining at a rate below the threshold the FAA set for green, which is 20 dBz. With older radars, to detect turbulence below the green threshold, the radar would need to be about 3 nautical miles away from the turbulence in order to see it in black reflectivity. Because the RDR-4000 is much more sensitive, it can detect turbulence at the same reflectivity level from about 15 nautical miles away. The turbulence detection capability on this radar is much more sensitive and accurate, so learn to trust it. Here are some items that might show up on the radar which are not weather. These pictures show a typical interference pattern, usually caused by military radars. They can also be from fighter aircraft, ground-based military radars, or ground-based radars like the Port of Seattle has installed, which sees ships in the harbor. These can appear as red, yellow, or green spokes on the display. They can look the same on the RDR-4000, or they can also look a little different because they are collected over multiple sweeps, motion compensated in the buffer, and separated into flight path and secondary returns. The interference will remain on the display until the source is gone and the motion compensation of the buffer data moves it behind the aircraft. We'll finish this section by talking about the gain control and its use. The gain control is active in all modes, but most of the time the radar will be in the auto or calibrated gain position. The calibrated auto position is the only position where the colors represent the FAA-defined reflectivity and rainfall rates as shown in the table. The auto gain setting provides a standard reference which all radar manufacturers must follow. Immediately after turning the gain control out of the auto detent position allows the pilot to select -16 to +10 dB of gain for analysis. Rotating the gain control counterclockwise decreases gain. Rotating the gain control clockwise increases gain. The gain setting has no effect on turbulence detection or display. After using gain to assess weather, it should be returned to the auto position. Using gain is really quite simple. Looking at a model of a storm cell reveals it is not as reflective at altitudes above the freezing level, but very reflective around the freezing level and below. So the gain knob is like a volume control on a TV or stereo. If the music is loud or very reflective, then one might want to turn it down. If the music is very soft or less reflective, then one might want to turn it up. So to put it in radar terms, some uses for gain are, if the gain is reduced to minimum in auto mode, what is left are the strongest cells in turbulence. Gain doesn't affect turbulence detection, so any cells remaining, and especially those containing turbulence, should be avoided. Reducing gain in heavy stratus rain can also help to identify embedded cells by looking for radar shadows. Increased gain is useful when looking at frozen storm tops and can be used in analysis mode when measuring the tops of cells. It's not a good practice to leave the gain control at maximum all the time, as may have been done with legacy radar systems. It could have unintentional results. With the RDR-4000, the pilot is going to see more weather, and that's a good thing. Weather at longer ranges, weather closer to the aircraft because of the 3D buffer and all the scans done at different tilt angles. Plus, the pilot is now looking at horizontal information and not just a single diagonal slice. Because the maximum reflectivity is always shown, increasing the gain will make all the weather appear more intense and also make more weather show up as flight path as shown in the two pictures. Here is an example of an unintentional result. In the picture, the reflectivity above 25,000 feet is below 20 dBz or black. So the secondary weather, green, yellow, and red, would be shown in the crosshatch pattern on the display because it isn't covered by any flight path weather. But if the gain is increased so the weather above 25,000 feet is now above the green threshold, it will be shown as solid green flight path weather. But remember, the flight path weather has priority over and will cover the more reflective secondary weather below it, making the weather look less intense and having the opposite effect of what was intended. Gain is mainly used to look at reflectivity information while performing analysis. And the best mode to look at raw reflectivity information is in man mode. In man mode, you will not have the unintended effects as just described in auto mode. Thank you. and enjoy the Honeywell RDR-4000 weather radar system.